Good morning. This is Unit 3, Day 1. We're going to start exponentials today. So we're going to let a and b be a real number constant. An exponential function in x is a function that can be written in the form of f of x equals a number times another number to the x power. So your variable is actually the exponent, where a is a non-zero, b is positive, and it's not 1. The constant a is the initial value of f, the value when x is 0, and b is the base. This b is our base. Identify the exponential functions. So our function is f of x equals 2 to the x. Our initial value is a number in front of the base. If there's no number in front of the base, then it is 1. The base is the number that has the variable as an exponent, so my base is 2 in this case. So yes, it is an exponential function. Why? Because it's in the form y equals, or f of x equals a times b to the x. Okay, let's try the second one. This one is 4x to the negative 3. So what does this negative exponent mean? So the initial value is a number in front of your base, and the base is the thing with that exponent. So my initial value is 4, but the base is a variable. The base is x. This is not an exponential because the variable is not in the exponent, so we're going to say no. This is a rational function. This is what we went over last unit. A rational function. And what it would look like is something like y equals a number over x to a number, okay? But that's an a over x to the n. All right, h of x, let's try this one. Is this a exponential? Our initial value would be 5. My base is a number with the exponent, so that's 2. And my exponent is a negative x, but that's okay. My variable is still an x, so we're going to say yes, it is still in the form. A, what do we say, times b to the x? Yeah. All right, the last one, number 4. It's asking us again. So our initial is 3, the number in front. Our base is 4. Let me just keep the same color. So this would be 4. But this is not a variable. E is not a variable. E is a number. E is like 2.7. So we're going to say no. E is a constant. It's like pi. It's actually a number, not a variable. All right, compute the exact value. It says without using a calculator. So what this is asking us is to substitute in x as 1/3. What this means is we're going to have f at 1/3 is negative 5 times 8 to the 1/3. 1/3, anytime we have a fraction, that means it's like a square root or a root. So this is going to be negative 5 times the third root of 8. And 8 is 2 cubed, so negative 5 times the third root of 2 to the third power. Anytime we have a root and a power that is the same, they cancel each other. And we're going to have negative 5 times 2, which is negative 10. This is how we compute it without a calculator. Go ahead and flip your page over. It says finding the exponential function form in its table of values. So determine the formulas for the function from values given in the table below. Values for 2 exponential functions. We have f of x is this one, g of x is this one. When we plug in x, we get this. at -2. When we plug in -1, we get this. To go from this to this, we're actually multiplying it by 2. 3/4 times 2 is 3/2. These would cancel, and 2 goes into 4 twice. 3/2 times 2 would give us 3. Sorry, I put 3, sorry, 2. 3 times 2 would give us 6, and 6 times 2 would give us 12. Okay, so we want it to be in the model f of x equals a times b to the x, where a is the initial value, what did they say when x is 0? And so this is when x is 0, we get 0, whatever a is, the y value. B to the x, where b is the base. Oops, B-A-S. Okay, so this is going to be where the pattern lies. We found our pattern. Alrighty. So this one is growing exponentially, and my initial value is going to be when x is 0. So this is going to be my initial value. My initial value is 3, and my b is going to be what I'm multiplying it by. This time I'm multiplying it by 2 each time. Multiply by 2 this time. Sometimes it's a fraction. This is growing, so this is going to be a growth formula. It's going to be bigger. It's getting bigger as we go down. So my function is going to look like f of x equals 3. A comes first. Times b is my base. That's what we're multiplying it by, to the x. This is going to be my function. Circle it. This is it. You're done almost. Now we have to do g of x. Now this one looks like it's getting smaller. 20 to 10. 10 to 5. It's actually getting smaller by multiplying it by 1/2, or we can say that we're dividing it by 2. Right? 10 divided by 2 is 5. 5 divided by 2. 5/2 divided by 2 is our 5/4. Alrighty, so this one is not growing. This one is a decay formula. My g of x is decay. It's getting smaller. My a is still initial. This is when our x is 0. So when our x is 0, my a is 5. And my b is the same. In this case, we're going to be dividing it by 2. So dividing. Instead of multiplying by 2, dividing by 2, which means it's going to be 1/2. I'm going to plug it in. It's going to be f of x equals a times 1/2 to the x. Put a parentheses around it, and still to the x power. This is your g of x, sorry. Alrighty, so exponential growth and decay. For any exponential function, f of x is a times b to the x, any real number of x. F of x plus 1 is b times f of x. For a greater than 0 and b greater than 1, we're growing. And it's going to be in the form of f of x equals something like 3 times 2 to the x. This is an example. It looks like this, 3 times 2 to the x. When I have 0, this is 1. 2 to the 0 is 1, times 3 is 3. So when x is 0, my y value is 3. When I plug in 1 into here, 2 to the first power is 2 times 3 is going to give me 6. It's going to grow very quickly, maybe something like this. It's never going to be negative. Even if you plug in negative numbers, it just means it's getting smaller. So we don't have a vertical asymptote, but we have a horizontal asymptote. Usually it is the x-axis. Sometimes, we can lower it or raise it. So my horizontal asymptote is y equals 0. That's the x-axis. My domain for a growth function, or e to the x, or any exponential, is usually going to be negative infinity to infinity. And my range is usually going to be, it goes from 0, we can't include 0, all the way up to infinity. Now decay is going to be a little bit different. Decay, we're getting smaller, but it's not going to go below the x-axis. We're going to have an example, maybe something like g of x equals 5. I think we had to like the 1/2 x. And when I plug in 0 into here, this is 1, and times 5 is 5. So when x is 0, it's at 5. When x is 1, this is going to be 1/2 times 5, which is half of 5, which is 2.5. And then it's just going to keep on getting smaller. It's not going to go below the x-axis unless we have a number out here, like -3 or something like that. It's going to have the same horizontal asymptote usually right here on the x-axis, which is y equals 0. My domain should be the same, negative infinity to infinity. My range should also be the same. It still goes from 0 all the way up. It just goes up the other way. So 0 to infinity. Alrighty guys, go ahead and flip that paper over. I want you guys to graph these, see what happens when you make a transformation. First, I want you to graph the parent function. So the parent function on each one is 2 to the x. The base is 2. So 2 to the x is, I'm going to make like an x and y chart for you. This is kind of what I do in my head. Y. Okay, this is for the base function. So just this one, f of x. So if I plug in 0, 2 to the 0 power is 1. Anything to the 0 power is 1. If I plug in 1, 2 to the first power is 2. If I plug in 2, 2 to the second power is 4. And it's going to grow that way. So at 0, we're at 1. At 1, we're at 2. And it's just going to keep doubling. It's going to get bigger, bigger, bigger. Okay? So this is the base function, 2 to the x. Oops. It doesn't actually touch this x-axis, okay? But if we're going to have x plus 1, what we're doing, remember when it's by the x, we do the opposite. So you think plus 1, it would be to the right one, but actually it's going to be to the left one. So this point right here is to the left 1 point, this point right here is to the left 1 point, and this point right here is to the left 1 point, like right here, okay? Okay, so this is the g of x. The red one is g of x, the 2x plus 1. 2 to the negative x, this is going to be a decay function. I'm going to graph this for you, the purple one again. Show me what the 2 to the negative x looks like. This is something you can use Desmos for. Go to desmos.com. I'm going to graph this one for you again, something like this. Okay, and show me what 4 times 2 to the x does. What happens to it? I'm going to write this for you. 0, describe how the transformation into the graph is given the functions. So this one actually, this plus 1 actually just makes it to the left 1 unit. That's all this changes. The part B, h of x, it doesn't shift it, but this negative x reflects the graph. Across which axis? Does it reflect it across the x-axis or the y-axis? I want you to write it here. Part C, those four in front of it, how does that change? I want you guys to tell me. Does it shift it up or down, or does it move it left or right? What happens? Does it make it grow quicker? How much quicker? Alrighty, we're going to go on to E. So E is just a number. What it is, it's a sum of a series. Sum of 1. Sum means we're just going to add them up. Plus 1/2, plus 1/3, plus 1/4, plus 1/5. You guys see, like 1/4 is bigger than 1/5, so it's getting smaller. And it's just going to keep going forever. Forever. And that's what E is. So the definition of E, we actually have a limit definition of this, is the limit as x goes to infinity, we're going to add them up, of 1 plus 1 over x to the x. So it also is an exponential. It goes to the x power. Any exponential function in this form can be written as the function equals a times e to the kx, where k is a constant. K is just a number. So we can make this exponential an exponential with e as a base instead of that number of b. Okay? If it's a growth function, then a is greater than 0 and k is greater than 0. If it's a decay function, of course it's the opposite. A is still greater than 0, but then the k is going to be less than 0. I don't know why I wrote it so high. Okay, this is going to be the opposite. The exponent is going to be negative. ln means natural log, and we have the base is e. It's a special one. We use it so much, we made a shortcut for log base e, and we say natural log. ln, natural log. Alrighty guys, I'm going to try a couple of these. So I want to just graph f of x first. F of x is going to be in purple. Okay, I tried. And this is just e to the x. E to the x looks like this. Okay. It goes through the point 0, 1 right here. This is 0, 1. And, sorry guys, the bell rang. Okay. Sorry guys. Alright, and I know that this point right here, when I plug in 1, I get e, which is like 2.7. So I know like this point right here is 1e, whatever e is. Okay, it's irrational, goes on forever. So I'm going to now graph e to the negative 2x. So how does this change? I know that this negative 2 reflects, or this negative, the negative part reflects across the y-axis. So we're gonna reflect this across the y-axis. It's gonna look like this, and the negative, or the 2 part, is going to decay faster. Faster decay. It's gonna go down quicker. Something like, let me just change color. This is gonna be in blue, okay? And it's gonna be something like quicker. Still goes through the same point, 0, 1. Alrighty, so that is gonna be g of x. G of x. It's good to label it. Now, a logistic growth function, the A, B, and C, the A, B, C, and K be positive, constant, with B is less than 1. A logistic function in X is a function that can be written in the form, this is going to be our form, C over 1 plus A times B to the X, or f of X equals C over 1 plus A. Remember, we can make this a function, an exponential with E. So times E to the negative kx, where the constant C is the limit to growth or carrying capacity. So C is the carrying capacity or limit to growth. I'm going to keep going. I know that's kind of confusing. I'm just going to show you some examples. I want you to graph this. So you can kind of look at Desmos and graph it. 18 over 1 plus 5 times 0.2 to the x. Okay, in order to find the y-intercept, we have to plug 0 in for x. So f at 0 is 18 over 1 plus 5 times the 0.2 to the 0 power. Anything to the 0 power is 1, times 5 is 5, plus 1 is 6. So 18 over 6 is 3. This is f at 0. So 1, 0, we are up at 3, maybe like 1, 2, 3, something like that. And my horizontal asymptote is going to be y equals 18 and y equals 0. Alright, so I just plugged in the horizontal asymptotes. Y equals 18 and y equals 0, which is the x-axis. And if you graph this, it looks something like, I don't know why this looks like this. So this is the horizontal asymptotes. This is the only one, or the last one I'm going to do. You guys can try the flu problem. If you have any questions, please ask me. Have a wonderful day.